Hi, I'm Macià Monfort, and I'm representing the Magnetohydrodynamic drive for water-based CubeSat propulsion. First, I want to start with what CubeSats are, because this is going to be an application for CubeSats, so it's important to know what CubeSats are. CubeSats are nanosatellites built of 10 centimeters side cubes, so they are really small. They are put into orbit as secondary payloads, and they are used in a variety of missions in education, scientific research, and industry. Here at the right, we can see an evolution of how CubeSats how many CubeSats have been launched per year, and the application of these CubeSats. I want to remind you that in the last year, more propelled CubeSats are being deployed. That is, that more CubeSats with propulsion systems are being designed, and these propulsion systems must avoid traditional high-performance fuels because they represent a safety hazard. This is because they need a pressurized vessel, and for example, for hydrogen, they may have leakage problems. So we want to avoid use them because a small mistake in a small CubeSat may lead to a huge explosion or may lead to the failure of a bigger spacecraft. So we want to use harmless fuels. There are many alternatives for harmless fuels, but I want to focus here on water propulsion, mainly because water is inherently safe. Water is not going to explode, and you can safely store water without pressurize it. And it's something that we really know how it's going to act in different situations, so it's really safe. And the alternatives that have been proposed or have been designed are cold gas thrusters, electric propulsion, solar systems, but I want to focus here on alkaline electrolysis. What is alkaline electrolysis? Mainly alkaline electrolysis is gonna be based on water electrolysis, which is the electrochemical process that decomposes water into oxygen and hydrogen, and it has some great advantages as that it provides a really high combustion efficiency with ISP higher than 400 seconds. This is the high-speed ISP specific impulse associated with this high-performance fuel, but we don't have this. We won't have these safety problems because we can just store the hydrogen and oxygen as water, and whenever we need thrust or to get some thrust or some impulse, we just start the electrolysis process. We store this hydrogen and oxygen, and whenever we need this, we just combust them and get the thrust. But we don't have to store the hydrogen and oxygen with the CubeSats. During all the mission, we can just have the water there. But it has some advantages, but it is also faced with phase separation problems, mainly because we are in microgravity, and this is a completely different environment than when we are on Earth. Basically, when electrolysis happens on Earth, the bubbles generated will just float to the surface of the liquid because of the buoyancy forces. But in microgravity, there are no buoyancy forces. So when the gas is generated, it's just gonna float around the liquid, and it's gonna be really difficult to separate gas from liquid. Some solutions have been proposed, as the one that we see here. This is the Cislunar Explorers. It was a CubeSat that was planned to be launched in Artemis 1 missions, even though they had some technical problems and they couldn't launch the CubeSat. And the proposal was basically to have was based on having the CubeSats constantly spinning, so they are inducing a centripetal force that will help that will generate some buoyancy forces, and liquid and gas will be separated, and then the gas will be used for the combustion and the propulsion system. Other solutions are the Cislunar was an inertial solution, and other solutions are the membranes or the diamagnetic, which use magnets. And the MHD drive is what we are going to propose here. The MHD drive is going to be based on the use of magnets. The Magnetohydrodynamic drive is going to use magnets, and we're going to aim to induce a rotation in the liquid, so we can use the same principle that the Cislunar used. And so basically, the MHD drive will combine gas production and separation in microgravity in the same device. We can see here how the MHD drive will look like. We can see here that this is the cathode, the anode. These are the electrodes needed for the electrolysis process to happen, and we're gonna have here a current intensity between those electrodes, and we're gonna place a magnet around the MHD drive, which is gonna induce a magnetic field in this direction. And when we have a magnetic field together with a current intensity, that is, we have electrons traveling or being pushed from one electrode to another within a magnetic field, a Lorentz force is going to appear on these electrons, and basically a Lorentz force is going to appear on the water in this volume here. So this force is going to be perpendicular to the magnetic and intensity vectors or the current vectors, and it's gonna induce a rotation in the liquid. So in this way, the bubbles that are generated between the electrodes are gonna just float towards the center of the device because of the angular velocity that the liquid will have. So basically, the MHD drive will act as a vertical phase separation thanks to the Lorentz force, and the main advantages of this device is that it allows a 3-axis attitude control. That is, we don't need to have the CubeSat spinning as the cylinders. We can just induce a rotation in liquid but without inducing a rotation in the CubeSat. Also, this is going to have no mobile parts, which is it's something that we aim to avoid in any space system design. So in this presentation, I'm gonna explain the model developed that will allow us to predict the performance and to help optimize the device of the MHD drive. As in every model, we're gonna start with some simplifying assumptions. We're gonna start saying that the effect of the gas-liquid interface is negligible. Also, that the liquid rotates as a solid rigid body. This is called the paddle wheel model, and is commonly used in internal combustion engines as a way to simulate the swirl of the gas. And this will be true for our model in all the liquid, except for the boundary layer, which will play a really important role in our development. So we are going to assume steady state and the Blasis conditions called for the study. That is that we have a laminar boundary layer and that we have flow in a semi-infinite plate parallel to constant on a directional flow. This may sound complicated, but it's basically that we have a liquid rotating, and this rotation is going to be parallel to the cylindrical geometry that we have. So basically, we have a flow that is parallel to the geometry that we have, and also that we have constant and directional flow, which is going to be the angular velocity. Lastly, we're going to assume that the bubbles effect on the ion transport and Lorentz force can be neglected. And with all these simplifying assumptions, we can just start the model with using these simplifications. We're going to start trying to find the angular velocity, which is going to be really important because it will provide the normal acceleration of it will help us to estimate the normal acceleration of the device, which is going to be the G factor for our MHD. So it's going to be really important to have the angular velocity of the liquid. We're going to start with we're going to try to find it based on a torque balance. And we're going to start with the Euler rotation equations. By steady state, we can just neglect this term, and the cross product of the angular velocity is going to be 0. So we just arrive to the conclusion that the torque generated by the Lorentz force must be equal and opposite to the torque generated by the shear stress in all the surface of the device. So we first want to estimate the shear stress and the torque that the shear stress is producing. So we're going to start with the shear stress expressed as a function of the angular velocity by a first order derivative. We can get this expression where the boundary layer thickness, which is this term here, can be expressed by Blasis conditions, can be expressed as a function of Reynolds and the characteristic length, and at the same time the Reynolds number can be expressed in terms of the linear velocity, which is going to be the angular velocity times the radius. So putting all these expressions together, we can get that the shear stress is going to be a function of the properties of water the characteristic length, and the angular velocity. Now, if we recall what a shear stress was, a shear stress is basically a force when it's integrated in a surface. So if we want to get the torque, we will just have to include the radius term here. So by integrating in a surface, we get the torque, and we can get this expression, which will depend on the geometry. We will have to substitute here the values that the radius that we're interested in, depending on which surface is, and basically the total torque, shear stress torque, gonna be the sum of the moment produced or the torque produced by the ceiling, the floor, the wall, and the electrodes of the MSD drive. Now we have an expression for the torque of the shear stress torque that depends on the angular velocity and on the geometry. And now we're gonna get the expression for the Lorentz torque. The Lorentz torque, as I said before, this would be the expression for the Lorentz force. And if we want to get a torque, we just have to include the values term here. Basically, we would see here, we are seeing here at the right the distribution of the magnetic field of a 3 mm magnet. So we would just have to make a volumetric integral of this times the current density between the two electrodes, and we will just get a torque but this volumetric integral. So we have the shear stress expression, which is dependent on the angular velocity, and the Lorentz force here. So we just can isolate the angular velocity, and we get an expression for the angular velocity as a term of the Lorentz force, the geometry, and the properties of water. Now we have the angular velocity. Our model is gonna continue by getting the gas production. Is gonna be just dependent on the electrolysis process. For each mole of electrons, we get 0.5 moles of hydrogen and 0.25 moles of oxygen, which are gonna occupy some volume depending on the temperature and the pressure. And also the current intensity between electrodes can be expressed. It's gonna be proportional to all to the potential difference, the surface area, and the conductivity, and it's going to be inversely proportional to the distance between electrodes. Also, we have the gas production now, so we want to get the extraction capacity. And to get this extraction capacity, we're going to have to use the drag buoyancy balance of forces in a bubble, which is going to lead to this expression that we can see here. And for us, the G factor is going to depend on the angular velocity. That's it. That is why it was so important to get that that approximation for the angular velocity, because it's going to give the terminal velocity of bubbles towards the center of the device in the radial direction. And also using rough correlation, we can get a closed form result for the terminal velocity. So basically, we have the terminal velocity of bubbles as a function of the radius and the angular velocity. And now we want to balance the gas production with the gas extraction capacity. So the gas extraction capacity is going to be basically the product of the terminal velocity times the surface of the interface radius. This interface radius is going to be somewhere around here, ideally, and we want to aim to have this interface radius smaller than the internal radius between electrodes. Because what would happen basically is that if we have our interface radius somewhere around here, gas would eventually start substituting the liquid in the space between electrodes, and this would lead to the electrolysis process eventually stopping. So first, what we're gonna do is to calculate this interface radius, which is the radius that balances the gas production and gas extraction capacity. And we're gonna see where it would lay, and if it lays, or if it's bigger than the interface, if it's bigger than the internal electrode radius, we're gonna have problems, and the electrolysis process will eventually stop because the extraction capacity is lower than the gas production. So this gas is gonna be just stored in the space between electrodes. On the other hand, if our interface radius is more than internal radius, this is what we are looking for, and we're gonna recalculate the the extraction capacity using the whole height of the device, it must be remarked that in first place we were using the distance between electrodes because we need to get the gas extracted from this space in the beginning. And if we can do so, we then just recalculate the extraction radius using the whole height of the device. So basically, we just have now our model developed. We have a way of estimating the angular velocity. We know the gas production by the electrolysis process, and we know how this angular velocity is going to affect the extraction capacity. So we can just balance it with the gas production, and we can have an idea of where the interface radius would be, and if this is going to lead to problems or if it's going to be just okay. So now, yeah, I'm going to show some results of that the model predicts, and also I'm going to explain some parametric analysis that we developed, and finally, we're going to show a proposed design that we developed thanks to all this parametric analysis for CubeSat application. Basically, the operating conditions that we are using are here. We are using an electrolyte, which shows a really low conductivity in experiments. Basically, we didn't know why this was happening, so we are using this low conductivity, which is an order of magnitude lower than the typical electrolysis process conductivities. Again, we don't know why this is happening, but we are going to use it because in any case, it's going to lead to an underestimation of the performance of the system. So if we get to increase this conductivity, all the predicted performance is just going to be better. So we are going to have here like a lower limit for this. We're going to use also platinum electrodes, platinum magnet, and a constant value between external and internal radius for the electrodes. We're going to assume that the bubbles will have a diameter of 0.25 millimeters, and we're going to use a pressure of 1 atmosphere. Again with with the conductivity, we may want to have higher pressures. However, this is the pressure that we are using in this, and again, in any case, it's going to lead to an underestimation of the performance, as all the moles of gas products are going to occupy a lot of volume when we compare it with a higher pressure. So this is going to complicate the extraction process. So if we just have a higher pressure, the extraction capacity of the device would be higher. So it would be, again, this pressure would lead to a lower limit of the performance of the device, which is what we are going to see in the next slides. Basically, the model predicts proportionality between Lorentz force and angular velocity, as we can see here. And for example, for an external radius of 0.23 centimeters, this would be the magnetic field that the simulation shows. And by doing the integral that I explained before, we can get an expression for the angular velocity. We can get some value for the angular velocity varying with intensity. Now I'm going to talk about the parametric analysis. First, for gas production, we can see that the gas production is proportional to the square of the external radius. This is basically, if we have a bigger MHD drive, we're going to be able to produce more gas, as the area of the electrode area is going to be proportional to the square of the external radius. And again, the current intensity is proportional to the area of electrodes. Also, if we reduce the distance between electrodes, the electrons are going to have an easier path from one electrode towards the other. So the intensity is again going to increase. So here we have two things that we want to look for, which is a low distance between electrodes and a bigger external radius, which is going to produce more gas. Now for the electrode distance influence, we can see here that it has a double effect. Well, we cannot see here. We can see here that it has no effect on the distance of electrodes, has no effect on the angular velocity, and this is going to be because it has a double effect. First, if we reduce the distance between electrodes, the intensity is going to be, or the current intensity is going to be higher. So the Lorentz force should be higher and the angular velocity should be higher. But on the other hand, if we reduce the distance between electrodes, the volumetric integral around the MAC drive is going to have lower volume. So less force is going to be applied on the water. So these two effects are balanced, and we can see that both effects cancel each other, and there's no influence of the distance between electrodes on the angular velocity. However, this distance between electrodes, as I previously said, do have an effect on the gas production. So if we have the same angular velocity and then the same extraction capacity, but we have different gas production, we're gonna have different interface radius. And we can see here a really low distance between electrodes will lead to a really high gas production, but the extraction surface is going to be really small because we have really small distance between electrodes. So eventually, all this gas production will not be able to be extracted. So the gas is going to just be stored between the electrodes, and eventually all the gas is going to substitute the liquid, and the electrolysis process is going to stop eventually. Now for the potential difference influence, we can see here that having a really high potential difference leads to a higher angular velocity, and also leads to a better extraction capacity. I wanna remark here that we cannot have a super high potential difference because it would lead to degradation problems in the electrolyte and the electrodes. So we want to have somewhere around 2.8 volts of potential difference to avoid all these degradation problems. And lastly, the magnet thickness influence. A higher magnet thickness is going to lead to a stronger magnet field and therefore to a stronger Lorentz force. So basically, it's something that we want to aim for, because if we have a stronger angular velocity, a higher angular velocity, the extraction capacity is going to be basically better. So we can see here that for a really small improvement in the, or for a 2 millimeters increasing in the magnet thickness, we can see here that the extraction capacity is significantly improved. Lastly, for CubeSat, we can, thanks to all these parametric analysis that we've done, the model, we can propose a design for CubeSat. For CubeSats, basically, for this design, we are looking for a maximum size of one unit, which is 10 centimeter diameter MHD drive. So basically, we are going to use a 4.4 centimeter external radius. We're going to maintain constant the relation with internal radius. We're going to use a distance between electrodes of 0.65 centimeters, which showed that the gas production wouldn't be high enough, so the gas extraction capacity wouldn't be able to extract all this gas. So this should to be a really optimal value. And lastly, we're going to use a magnet thickness of 5 millimeters approximately, because we saw that the magnet allowed to improve our system, but without increasing a lot the size. So inputting all these parameters into our model, we get that the angular velocity would be around 132.4 degrees per second, that the interface radius would be 1.63 centimeters, which would be somewhere around here. And we can see at the right here, the magnetic field that the magnet of 5 millimeters will produce in all the geometry of the device. And we can see here the volumetric Lorentz force applied, and the Lorentz force is only going to be exerted where we have current intensity, which is going to be in the space between electrodes. So we can see how the geometry would look like, and we are using aluminum for the box of the MHD drive, and the mass of this would be 0.25 kilograms, including the electrodes and the magnet, and without considering the water. And this gas production that we have here would allow to have a 0.33 meters per second delta V per hour. That is, every hour we would be able to produce all the mass needed to get this 0.33 meters per second delta V. And one we will have to wait 1 hour to produce and store this mass and then to combust it as an impulse. And basically, as an impulse, we're gonna have different impulses. We are not gonna have a constant thrust over time. And this will be for a 14 kilogram CubeSat. So we will have a smaller CubeSat. The delta V will be higher, obviously. So conclusions for our presentation: the model predicts that the energy drive is feasible for CubeSat propulsion. That is, that the gas production the gas produced can be extracted from the device, and then it can be used for the propulsion. So and within the size range of a CubeSat, we found a quite optimal design that could be used for CubeSat application. The model predicts a 0.33 meters per second impulse per hour that could be provided from our design for our 40 kilogram CubeSats, and this will have a mass of 0.25 kilograms. And lastly, I want to remark again the two great advantages that this design has, which are that it allows a 3-axis attitude control, so we wouldn't have our CubeSats constantly spinning, which may not be desirable for every mission. And lastly, we don't have any moving parts, which is going to be something really positive in any space system design. Finally, I wanted to thank the Georgia Space Grant Consortium, which provided me with a travel award, which allowed me to present this in Knoxville during the AIAA Students Conference. I wanted to thank the Santander scholarships that allowed me to be studying 1 year abroad in Georgia Tech. And the authors, me and Álvaro, would like to thank Professor Katarina Brinket for her support to the ongoing experimental validation of the model that I presented in this document. And lastly, that the MHD drive I would like to remark that the MHD drive is a technology patented by the Georgia Institute of Technology. And this is going to be a video for YouTube. If you have any questions, if you want to let them in the comments, just feel free to do so. And thank you for listening.